It was going to be next week, but obviously.
Is that the 15% exam? That's the 15% exam?
Yes.
Alright.
Okay. Now this is genuinely useful. Basically what this, we'll see we'll get into what it's for. So what we're going to do is, there's a bit of blah 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 blah. Okay, so the first, I'm going to write down something and then we're going to say what the hell is that all about. I'm going to write down, I think, I'm going to write down dy, we'll explain where this comes from. Dy is equal to f dash of x by, I can do dx or delta x, it doesn't really matter, same difference. Right, and I'll explain what this is. So what this is if you really want to approximate a function using a tangent, this is kind of one of the ways that you do it. And what it does is it approximates the change in a function using the tangent. So we'll see where this kind of thing comes from. And we'll put it in the, hopefully we'll get it in the correct kind of context. So the function just makes something that maybe increases, something like that. Okay. And what the context is going to be is this function. Remember earlier, this is a little bit like the area is a function of side length. And those things that you put into the function in context, if you've got any kind of a formula at all, so I mean any kind of a formula, I don't know, I just, do you know any formula that you use at all? Anything?
Pi r square h.
Huh?
Pi r square h.
Right. B is equal to pi r squared h, the volume of a thing. So this is a formula for calculating a volume. It's also a function, the volume is a function of the radius and the height. Now in context what we're going to imagine is that functions are formulas that we use to calculate things, and what we do is we put in, we measure these two things. Fair enough? And we bang them into the formula. That happens all the time. Measure something, bang it into a formula. Fair enough? Right, that's the context. So imagine that this is our measurement and we're going to call it x0. So this is some measurement. Now for this we can think about maybe the area of a square. So we measure the side length and we square it. Unless you're counting something, what is guaranteed when you make a measurement?
To be right, I suppose.
That it'll be right? You're guaranteed it won't be right. In a mathematical sense, when you make a measurement, you will not be right.
To approximate? Will we be approximate?
To be approximate. What do you have? You measure something. You can have a length, but like say if you want to measure the length of, say if you've got a rectangular kind of piece and you measure the length, and you measure the length with a what? A ruler. Are you getting the exact length with a ruler? No, you're only getting a rough estimate, an approximation. So what is there when you measure? Error. Guaranteed. Mathematically guaranteed there's an error. And now I say mathematically guaranteed, in a mathematical sense it is. In the real, okay, so let me explain. Suppose, even, say for example there's a ruler, and imagine you've got a 10 centimeter ruler for whatever reason. Now there's all kind of physics things coming in that we're just going to not, I'm talking maths, we make up our own thing. In physics, sure, there's all a million different things happening. The length of the ruler depends on the temperature.
Materials.
When you go down to really quantum, beyond microscopic, there's no straight edge, it's like it's all over the shop. You go down really, down even smaller, it gets even, every length is a multiple of a tiny, it's just a mess. But imagine an idealized ruler, okay? So imagine that it's dead straight, and it has some length. And the length in mathematics would be a real number, which is just a decimal. For this to be exactly 10 centimeters, I'm going to use meters here. So the length would have to be 0.10. Total precision in the centimeter. Total precision in the millimeter. In the micrometer. In the picometer. I'll be making up the next one. I think it's Yako or something. Femtometer. Imagine you can make it. You can't. You know you can't do it that accurately, yeah? But if you could, once you get down to here, the numbers after this are pretty much random. Like, you can't get it that accurate. So for it to be exactly 10 centimeters, so once you get down to here, what's the probability that the next digit is 0? Huh? 1 in 10. What's the probability that these two are 0?
100.
1 in a
1,000.
10,000, 100,000, 1 in a million. What's happening to these probabilities? Smaller and smaller and smaller. So the probability that it's exactly equal to 10 centimeters is 0. There has to be an error, unless you're counting. And basically the chance of you getting it exactly 10, it's no, right? I can dwell on that a bit longer, but I really don't need to. Except when you make a measurement, doesn't it? I mean, if you're using a meter stick, what's the error? Guaranteed, well, not guaranteed, but what's typical error when you use a meter stick? Zoom in. You can only measure accurate to this. What's that? 1 millimeter. So there's going to be that's an instrument error, okay? And then you got other errors. So there's going to be an error. So for example, you want to measure the width of this. You can do it accurate to a millimeter. So you're guaranteed a little error. It's going to be a small error. If you can't do it accurately, it has to be a small error for what we're going to do to make sense, okay? If you can't measure things accurately, you need to start again. Now, the way I've drawn it, the error is positive. Does the error have to be positive?
No.
No. It could go either way. I won't draw it the other way, but it can't go either way. This is the this is the true value. Oh shit, no. This is the calculation, and this is the true value. Calculation. And this is the true value. In context. So what happens is we measure something, we bang it into a formula, we bang in our calculation. Calculation, sorry, that doesn't make any sense. Measurement. Sorry about that. That's your measurement. You bang your measurement into your formula, and that is what we might call, that's what I want to call the calculation. So for example, the area of a square, you measure the side length, you square it, you get the calculation. Does the error in the measurement cause an error in the calculation? Yes. And this is what we're interested in here. So if we look at the true value, we go up from here and across. I'm just going to call this F subscript true. So this is the true area in context, this is the true area. And the difference between these two is the error in the calculation, delta F. So error in measurement causes error in calculation. You don't measure your side length accurately, you're not getting an accurate calculation of the area. So what we're going to do is to approximate this, we use the tangent. So if you draw a tangent here, so do as best as you can. Hopefully you got a bit of curve on this. I don't really have enough. I'm going to have to exaggerate this. So this is the tangent. Okay. You don't want to. You want a little bit of. Ideally, it shouldn't track it exactly. Maybe it goes a little bit underneath it. Maybe if your tangent is kind of really straight here, maybe just exaggerate and underestimate. Make a little triangle here. Now this little thing here is what we're going to call, now it's called dy up here, and sure we'll call it dy here as well. That is according to the tangent at the measurement, that is an approximation of the error in the calculation. Can you see that dy is similar to delta f? I mean, I could draw delta f just from here to here, same difference. They're similar, yeah? Yeah. Could you tell me a scenario where they'd be very similar? Something about the error.
The error being close to none.
If the error is small, the tangent and the curve are very, very close together, and these two are a very, very good approximation. What we're doing, if the error is big, there's going to be a big disparity between the true error and this, what we call the differential. So we'll be assuming the errors are small. If we do a little bit of maths over here, what is this? How do we get the slope of the tangent? Differentiate. So the derivative of this is the slope of the tangent. Now this is dy. This is the error delta x. What is another way of getting? If you have those things in front of you, how can you get the slope of the tangent? The slope of the green bit.
You do Pythagoras.
Try it. Say it again.
You do with
So given the dy and the delta x, how do you get the slope?
Differentiate the x to.
You have that. But if you have this dy and this delta x, how do you get slope? What's the roughest sense of slope you have? Steepness, but go on, do it.
Hypotenuse.
No, the hypotenuse didn't come into it. Roughest sense of slope?
the tan of
The rise over the run. The tan of the angle.
Oh,
Yeah. So dy over delta x. So multiply both sides by delta x and you get this. So the error in f is approximately dy, which is the derivative at actually x0 times delta x. So if you want to estimate the error in a calculation, you differentiate the thing you're doing the calculating with at the measurement times the error. And it's like the rate of change of f with respect to x times the change in x. Therefore, this is approximately the change in f. In other words, the error. Okay. Right. Okay. So if we've got a function of two variables, I can't really draw that picture. But what we do is we say that there's two. Now I want to change notation a little bit down here. So if you've got a differentiable function of two variables, we are going to have two differentials, delta x, delta y, and you're going to have dz estimating this. So what you're going to do is you're going to have, I said I'm going to change the notation. So put this little x up high, put this little y up high, put this little x up high, put this little y up high. Now what this is basically doing, and we'll do something with it in a moment, is saying, okay, if you've got a function of two variables means two things that we're measuring. Two things that we're measuring mean what?
Two errors.
Two errors. And what we're going to do is we're going to kind of assume that basically the errors don't really interact. So what I mean by that is you're going to have errors in the calculation of the volume from measuring this, and you're going to have errors in the calculation of the volume from measuring this. You're just going to add them together. Now it's kind of a little bit nonsense, but it's rough, and it's if the errors are small, it's a little bit accurate. It's fairly accurate. So what you got here is, if you've got z depending on two variables, it's approximately given by what's called this differential, and this is basically errors in z caused by, so errors in your calculation due to errors in the measurement of x, plus errors in your calculation due to errors in the measurement of y, and basically just do this thing twice, derivative by error. There's a derivative, there's an error, there's a derivative, there's an error. So you basically add them together. Now this is a thing that is not going to, well, actually we're nearly there, we're not there yet. Okay. So this is a basic setup. There's a few things we haven't taken into any account, errors being positive or negative. We have to deal with that. Okay. So we'll just leave that there for a second. Okay. So we'll move into, now we got z in terms of x and y, but imagine we got some property in terms of variables a and b. So imagine we have a physical property p in relation to two other variables. So p, this is like volume, for example, depending on a and b, say r and h. So we measure a and b, we record values a0 and b0 with associated errors delta a and delta b. These errors usually come from your measurement device. And you, like, so for a ruler, it'll be a millimeter. For some calipers, it'll be, I don't know, 0.1 of a millimeter. Then the better one, that is a micrometer, it'll be so many micrometers. A digital clock, a digital stopwatch, it'll be maybe a centisecond, and you have to add in your reaction error. Other things, so for example, I know you don't do electronics. If you're measuring, say, voltage with a voltmeter, the way they're set up is the error is a percentage of what you get. So if you get 3 volts, it'll say maybe the error is 10%, so the error in the calculator, or the measurement of the volts will be 0.3. But as you measure it, that's pretty much it. Temperature, so temperature is probably, I don't know how accurate those yolks are. I mean, any kind of measuring thing should come with, we have to calculate the error or estimate it. Okay, so what have we got? We keep track of the errors. We want to do this. So the thing is that if you've got your error, your true value is between a minus the error and a plus the error, and similarly the true value of b is between. Actually, these should be little zeros. I won't worry about this too much. Okay, I'm going to write down something, and you're going to kind of come with me on this. All right. So, one of the problems with this is the errors can be positive or negative, and the derivatives can be positive or negative. And if you just flat out calculate this, maybe. Like if you don't think enough, you might take the errors to be positive. This could be plus and this could be minus, and you get that the errors cancel out. But that shouldn't happen. So like if this is positive and this is positive and the errors cancel out, you're not guaranteed that could happen. Maybe this error is positive, but maybe this error is negative. And so you get a plus plus, maybe minus minus, and you get you don't get cancelling. You get a way worse situation. So what you're always going to do is take a worst case scenario, and how you take a worst case scenario is just make everything positive. And this is how we do this. So the error in the calculation is approximated by, what we're going to do is we're going to take the absolute value of this and maximize it. So we're going to call this dp, the bars for absolute value max, and we're going to make this formula as simple as we can. So we're going to assume that the errors are positive, and we're going to take the derivatives to be, we're going to make them positive as well by doing the absolute value. So we're going to have differentiate the thing we're calculating with respect to the first thing we're measuring times the error in the first thing we're measuring, plus differentiate the second thing, differentiate the thing we're calculating with respect to the second thing that we're measuring times the error in the second thing we're measuring. And this formula you need. I'm not putting it on the paper. Because you need to kind of understand it's rate of change by change. Rate of change by change. So this is the rate of change of P with respect to A times the change in A. So this gives a change in P. In other words, the calculation is changed from what we got to the true value, and that represents an error. I'll write some small things underneath. This is error in calculation. And these are errors in measurement. And this yoke, and similar to this thing, this is the partial derivative, partial P, partial A. And the bars mean absolute value. If you get something negative, make it positive. This is actually genuinely useful because if you have